Right. Sound check. Good. All right. I think we're all set. All right, welcome back. All good? Camera. Start off, any questions? Now that you've had the night to let this stuff sink in. All right, so let's continue on. So we left with our calculator circuit. Just a very quick review of what we did yesterday. I'll just zip through the slides. A review of our schedule, daily schedule. Everybody should have access to the Git repository, which is your access to everything. And I saw most of you joined the Slack group. That's great. So we did a quick review of what digital logic is all about, logic gates, composing gates, some arithmetic circuits, played around with NAND game, discussed tiny tape out, FPGAs and ASICs, played with Walkwe and designed a circuit that way specifically for tiny tape out, and then I introduced the MakerChip platform and transaction level Verilog, and we just did some basic combinational logic with TL-Verilog. All right, and this is where we left. So we beat combinational logic to death. Now it's time to introduce time. So let's talk about sequential circuits. So we're doing this calculator circuit. So far we've got 4 arithmetic operations and an op input that selects which operation we want. A real calculator, you perform the operation. The result of that operation becomes the operand for your next operation, right? So we need a loopback path from the output to feed back as the val1 input. Right? So if we just connect these up directly like this, we have an issue. This circuit is not stable. All right, we're going to have values at the input. They're going to propagate through the output. You know, the signals are going to propagate through the various paths in the network, and the output is going to adjust as that logic settles. So it may transition several times before it actually settles on the proper value, the stable value. That value is going to propagate around. If we just let all of that random transitioning propagate through, val1 is going to change, that new change is going to propagate through, and our circuit's not stable. So we need to carefully sequence the circuit by introducing a clock. By adding a clock, we can allow the data to propagate, stabilize, and then only once it's stable, drive it forward. Okay, so every clock cycle, we're going to take the data from the output, send it back around as val1. So every clock cycle will do a new computation that's based on the old computation, right? I don't think any of this is new to you. I think you've all done sequential logic before, but just to sort of talk through the nature of sequential logic. So this is the change that we will make to our circuit. So everything that we do in transaction level Verilog, TL-Verilog is going to manage the sequential elements for us, the flip-flops. Okay, everything that we're going to imply in our design is a D-type flip-flop, which is simply taking the input and carrying that forward to the output. There are other types of flip-flops that incorporate logic functions. Logic synthesis is very good at taking the functionality of our circuit and optimizing it to choose logic gates that are optimal. If it's optimal to choose a different flip-flop type that incorporates some of this logic, logic synthesis will do that. So let's see. So in the waveform here, Val 1 and Val 2 perhaps are driven by a clock edge. Val 1 certainly is. It comes straight from the flip-flop. And let's say Val 2 also is driven out of a flip-flop. Those transitions will happen fairly immediately at the clock edge. The output's going to take time. The values have to propagate through. So in this period, output is not stable. And then it will stabilize on 5 plus 3 is 8. And be stable for some time until the clock comes along and captures that value to carry it forward, right? So the, a somewhat realistic view of the timing here might look like this. Simulations are using a zero delay model, which means they're assuming that the gates are infinitely fast. They're modeling only values at clock transitions. So while this may be the reality of the timing, the zero delay model is going to represent that as things happen instantaneously. The waveforms that we look at are going to look like this. So there's no inherent visible representation of the time delay through the combinational logic. Perhaps a more realistic view of things, I guess we'll look here on the right. So this is an example of, let me turn on the laser pointer. So this here is an example of a circuit that would glitch. Perhaps, let me think, what's the scenario here? So this is our familiar full adder circuit, right? And we've got these two exclusive OR gates. So any change on any of the inputs is going to toggle the output. That's the nature of an XOR, right? So if, for example, these might be driven straight out of a flip-flop with similar timing, and maybe from one cycle to the next, the values of A and C transition. So the transition of A is going to propagate through this XOR to transition this, which is going to transition through this XOR and transition this. C is going straight to the second XOR gate and transitioning S. So when these two transition simultaneously, the C path is going to be faster, it's going to toggle S, and then the A path is going to come along and toggle it back. Okay, that creates what's known as a glitch on S. Something like this, right? So the reality of the signal, the clock is not perfect, and the transitions on foo take time and are glitchy and imperfect. So the reality might look like this. What you're going to see in the zero delay model would be this. Okay, so this transition, for example, all of this happens instantly with a zero delay model, and we see it in the waveform as just a high value. Okay, so when we're thinking and reasoning about digital logic, we're only concerned with the stable values, the logic functions at a Boolean level. We don't need to worry about delay. It's the nature of digital logic is you design with certain constraints to guarantee that the timing of the circuit works, and the logic function that you describe is actually how the circuit is going to behave, as long as you design within those constraints and the tools help us meet those constraints. We just need to think about the Boolean logic functions. So that's the last I'm going to say about anything below the level of the Boolean functions that we're encoding. So the nature of sequential logic, I don't actually know that this slide is very helpful to the thought process, but it kind of makes a point and then you can forget it. I think it's sort of mandatory that every introduction to sequential logic starts with this picture. Your overall circuit can sort of be decomposed into combinational logic and the sequential elements. Okay, so any circuit, this picture represents any digital sequential circuit. All right, it's a sea of combinational logic. It has inputs and outputs, and every cycle, the state of the machine captured in the flip-flops drives the combinational logic. The combinational logic drives the inputs to the flip-flops. The clock comes along, it captures the next state, that becomes the state, and the process repeats. Any sequential logic, it's important that we can bring that logic up in a predictable way. So we need to be able to turn on the circuit and get to a known state. That's the purpose of reset. Reset is generally following a protocol that it's going to be asserted for some minimal number of cycles and then deasserted. Often we use a negatively asserted reset signal, reset N or reset bar, or whatever you want to call it. That's kind of arcane based on, I don't know, historic constraints. With TL-Verilog, with MakerChip, we use a positively asserted reset, design all our circuits that way. Let's see. So the flip-flops here represent the state of your system. And so one way to get the machine into a known state is to put a reset condition on all of these flip-flops, as we've done. I guess we haven't looked at already. So drive a reset into this mux to select a known value at the input, usually 0, not always, and capture that value in the flops. So immediately after reset, the first clock edge during reset is going to get us into a known state, and then we can resume execution when reset deasserts. It's not necessary to reset every flip-flop in the circuit. Many design teams will use a methodology where every flip-flop is a reset flip-flop. If you're designing with FPGAs, on some FPGAs, all the flip-flops have reset support. But it's not necessary to drive reset to every flip-flop. And as we go through, you'll see, you know, sort of how to think and reason about where we need reset and where we don't. Essentially, anywhere there's architectural state, you need to reset that state. Other flip-flops are just carrying values through, and we can rely on this reset window to, you know, reset a subset of the states, and then rely on this reset period to propagate those known values to stabilize the rest of the circuit. So let's look at a simple sequential circuit. So this is a circuit that computes the Fibonacci series. The Fibonacci series starts out with 2 1s, and in the circuit implementation, every clock cycle, we're going to calculate a new value in the series as the sum of the previous 2 values. So 1 plus 1 equals 2. 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 3 is 5, etc. So that's going to generate. Our circuit is going to generate this waveform with 1, 1, 2, 3, 5, 8. That's the number here. Send that number through a flip-flop, and that's the previous number, 1 cycle earlier. Send that through a flip-flop, that's the previous number. So every cycle, to compute the number, we're adding the previous number and the previous number. Okay, so this is our Fibonacci circuit. Anybody notice anything missing? Yeah, we need to reset this. We just talked about the fact that every sequential circuit needs to be reset to a known state. Known state for this circuit, we can reset this to have the previous number and the previous number be 1. That'll initialize us, start us off. And we can get 1 here and here by injecting a reset value of 1 in number, right? And then, as I said before, we rely on the clock, which will be running during reset, to propagate that 1 forward. So after reset, we're going to have a 1 here, here, and here. Okay, importantly, we have a 1 here and a 1 here. And then we deassert reset, those 1s get added and become a 2, and the circuit continues. Make sense? In TL-Verilog, we can express that circuit with this single line. So the number here is, first we deal with this mux. So if reset 1, else the expression for this adder, right? So if reset, then 1, else the result of the adder, which is the sum of previous number and previous number. Good? So we had no declaration of previous number. We had no instantiation of a flip-flop. We had no instantiation definition of the previous, and this flip-flop. That's all implied. Okay. At this point, we can refer to this as previous and this as previous. We'll see later that's not exactly what they mean, but in this context, that's what they are. So if you don't have your laptop open, open your laptop, open up MakerChip, and this exercise is to code a very similar circuit, slightly simpler, but same idea. So the Fibonacci series example is over here on the right, just for reference. Your exercise is here on the left to design a free-running counter. Okay, so the counter, similarly, on reset is going to reset to a 0. And every cycle thereafter, it's going to add 1 to that counter. make sure you have the definition of reset from the starting template here. The star reset here refers to system Verilog signals. So this macro gives us this module definition with the reset signal. And this is a reference to that signal. So you're really just sort of putting that reset in a TL-Verilog namespace. It's notation for in TL-Verilog context. That's your notation for a system Verilog signal. In TL-Verilog context, you would use a star. So, you know, here in Verilog context, you can just reference it as reset. Everybody good? Almost. So this is my solution. So our count here, first the mux, if reset, 0. And here I'm just using the shorthand. This is a 32-bit value, and if I don't specify, 0 is a 32-bit value. To be explicit, I could say 32 tick, and then whatever base I choose. Otherwise, so the other leg of this mux, the sum of the previous value of count and 1. And again, I'm using shorthand, but to be explicit. Okay. One thing to point out, just because it can be confusing, it's a common mistake to forget the flip-flop and recirculate the value immediately without this flip-flop here, which would be this, without saying it previous. If I compile that, I'm going to get this very confusing message. Settling region, or settle region, did not converge. And that's going to point me at the Verilog version of the count signal name. What that means, settle region did not converge, is that the logic has a combinational loop. It never stabilized, right? So like I was talking about before, in the calculator circuit, if we loop that calculator output back to val1 input, the logic doesn't settle. That's what this message means, just in case you see that again. So let's do the same thing now with our calculator, right? We looked at the picture before. Now we'll implement this. So hopefully everybody has saved their calculator circuit locally in MakerChip. You can go to the project menu and open. And I don't know if I saved mine or not. I think I did. I guess not. But you can find the file that you saved, open it up, and continue on. At that point, your changes again will auto-save back to that file. When you edit the file, the browser is going to prompt you, because at that point you're trying to edit a file in your local file system, which is a privileged operation. It needs your permission to edit the file in your local file system. Okay, so go ahead and implement that circuit. Let me see if there's anything to talk through here. Yeah, so each cycle, val 1 is the result of the calculator in the previous cycle. We need to add a reset because now we have a sequential circuit. So on reset, we'll reset the output value just like your calculator would when you turn it on or when you press clear. We'll reset the output value to a 0. So that's this path. So if you had any trouble with it, just look up here. I'll walk it through. Let me look ahead too. Many of you coded this differently than I did, but not necessarily wrong. So let me just look ahead and see what we depend on. Yeah, I think in general, as I go through my solution, even if your solution was right, update your solution to look like mine just to make the rest of the exercises go smoothly. So just talking this through, there's basically two parts to this. The one part is the recirculation of output, and the other part is factoring in reset. So I'll do the recirculation first. Okay, so it used to be that val 1 was essentially dangling. We had the random value hookup. We're going to remove that hookup and provide the recirculation. So that's up here. No longer driving that randomly. Instead, I'm driving that with the previous value of out. Okay, it's that simple. That gives me the flip-flop. Many of you got rid of val 1 altogether and just used previous out for all of these. That's fine too. Again, code it this way so we have the val 1 signal to refer to later. The other part of this is reset. So for reset, the logic as drawn here is factored into this mux. Essentially, reset you're always factoring in as a multiplexer in front of a flip-flop. We already have a multiplexer in front of the flip-flop, so we'll just include it as one of the choices for that multiplexer. You could define a separate multiplexer right here. It would do the same thing. So I'm going to define it all in that multiplexer. Reset needs to be highest priority, right? If it's not highest priority, there's no guarantee that we actually reset our circuit. Highest priority means it has to be at the top of our chain ternary operator. So we need a case for reset. If it's reset, we want to use an 8-bit value 0. Okay, so again, it's that simple. We just need an extra case in our mux. Okay, versus yesterday, I had to type my example all over again since we're on a different machine. I took a shortcut and didn't bother assigning the signals sum, diff, and so on. I just put that right in line. Either way you've done it is fine. You can certainly keep the structure that you had with a sum assignment. It's just my shortcut. Any questions about this? Yeah. Now it's a 5-to-1. How is it possible to have a 5-to-1 multiplexer? Why shouldn't you be able to have a 5-to-1 multiplexer? Yeah, so logic synthesis, you know, it's possible that the library that logic synthesis is working with has perhaps a 4-to-1 mux, right? Generally, it's going to be working with lower level things. But it's up to logic synthesis to take the logic as we've described it and map that to the physical cells that it has available. So this doesn't mean there's a 5-to-1 mux cell. It just means that's the logic function that we want, and then it's up to logic synthesis to make that happen. Any other questions? So I'll just give you a minute to update your code to this structure. Okay, so that was a quick primer on sequential logic. You know, we'll use sequential logic more. You'll have more of a chance to play around with it. I'm going to shift gears now to pipelines. So here we're looking at a computation of Pythagoras' theorem. Okay, so we're computing this distance c as the square root of the sum of a squared plus b squared, right? We all know this equation. So the direct implementation of that as combinational logic is here. This is a fairly deep computation, right? We have to square numbers, add them, take the square root. We're not going to be able to do all of that computation in the period of the clock, most likely. Okay? So we have to partition the computation so that we're doing some logic in one clock, more logic the next clock, more logic the next clock. So simplistically, I've just divided these three steps into three pipeline stages by putting flip-flops between each computation. Square root itself is a very complex computation, and realistically we would not be able to do that in a single cycle, but this is just an example. Let's pretend. So we've got our three-stage pipeline to do these computation steps. So before, you know, without any flip-flops, we're assuming that we can do the entire computation in a single clock period. If the clock is running faster, we can't. So each of these steps is accomplished in one clock, and it takes three clock periods to do the whole computation. Okay. We see this in the real world in any number of ways, right? Here I've depicted an assembly line for a pretzel, or assembly line's not the right word, but you know what I mean. So in the first stage here, we roll the dough, and then we go on to the next stage and we twist the dough. And while we're twisting the dough, we're rolling dough for another pretzel, and then things shift. We salt the pretzel. While we're salting, we're twisting, we're rolling. Okay, and then we start baking it, we finish baking it, we've got a pretzel. So we're doing 5 operations on the pretzel at a time. The whole, you know, maybe this takes, who knows, 10 minutes to get through from start to finish, but we're doing 5 pretzels at a time, so we're doing a pretzel every 2 minutes. Okay, so that's the concept of pipeline, is to overlap operation, overlap execution. The faster you run your clock, the faster the throughput, but the less you can do in each step, so the more you have to overlap. So in this picture, the pipeline is the conveyor belt, and we'll use the term transaction to be the pretzel, the thing that's moving through the pipeline. So this is how we look at the pipeline logic, thinking about it in sort of an RTL mindset. When you use transaction level Verilog, you design your logic with a transaction level thought process. You give yourself the context of a pipeline, and the pipeline has pipeline stages, and within those pipeline stages you have logic, right? So I'm not depicting the flip-flops in this representation of the model. Instead, I'm giving it context, and from that context I can imply the flip-flops. All right, if I assign a squared in stage 1, but then I use it in stage 2, I need a flip-flop to get me from stage 1 to stage 2. You can very directly translate a diagram like this to code. Okay, so this is the syntax in TL-Verilog. The context, basically by placing your logic in context, then you derive from the context the flip-flops. Okay, so in this representation of the pipeline logic, I'm not expressing the flip-flops explicitly. So that makes my logic not just easier to express, but easier to modify, and we'll see that coming up. So the expression here, you're saying, I have a pipeline called calc. It has stages 1, 2, and 3 with these logic expressions. Okay. You need the context of a pipeline to have the pipeline stages, right? The pipeline and the stages go together as one construct, basically. So the nice compact expression, the flip-flops being automatic, is a nice thing. What's more important about this expression of the logic is that it's easy and safe to transform this design. So it's very rare in the real world that you are writing code from scratch. More often, you have a design that worked in a previous generation, and you need to implement it, re-implement it on different technology. That new technology has different constraints. You might be, you know, the timing of the logic elements is different. You may be designing for a different target clock speed. And so, you know, in various ways, right? Timing, area, power, your logic may be laid out differently. You might have different power constraints. You might have different timing requirements, performance requirements. Generally, the one that's the most painful is the timing, but they're all painful. But in the case of timing, right, perhaps this is my original circuit on top, but in my new context, maybe this logic is distributed across a chip, and the squaring of A happens in one corner of the chip, where the adding them together is somewhere else. I might need an extra cycle to get from where it's produced to where it's consumed. So I need this dead time, right? And similarly, maybe square root is off in some other corner. So let's say this is the circuit that I need to implement in my new generation. This is what I have in my old generation. Making that change is as simple as just changing the stages for the operations. So I've moved the squaring of A to stage 0. I've moved the square root from stage 3 to stage 4. Okay. Now, the most important thing about this is that this change, since I know that all I've changed is the staging, is 100% guaranteed that I have not changed the functionality of my circuit. Okay. It's possible that I broke the implementation. For example, if A is not actually available in stage 0, it's available in stage 1. This circuit works. Perhaps, may or may not be implementable, but at least at this level it's not broken. Whereas the one below is broken because I can't use the signal before it's assigned. But that's a broken implementation, not a broken behavior. Right? The behavior of this lower circuit is the same and hasn't changed. Pipelines are conceptually infinite in both directions. You can have logic in stage minus 1028. No, you can have logic in stage minus 1028. You mean the one up here? Why am I showing stage 0? Yeah, just... Yeah, so the flip-flops are going to exist wherever they're needed, right? So the existence of these flip-flops, the existence of stage 0, just depends on the assignment of A and B. Where are their assignments? Right. Right, so the pipelines are conceptually infinite. All signals exist anywhere they're needed. So I'm showing flip-flops implies that I've implemented this. The implementation and the existence of those flip-flops just depends on the surrounding logic. Right, so if... Yeah. Right, this expression here, let me get my laser pointer back. This expression here is this box. So that's all I'm expressing. The flip-flops being implied, I drew in my diagram, but they're not really explicit in the code. They only exist if and because there's an assignment of A earlier. Right, so yeah, this code doesn't necessarily mean there's a flip-flop. It depends. I'm just drawing it stretched out to match, this one. But right, if the assignments of A and B are also in stage 1, there's no need for flip-flops. They won't exist. So just the same slide we had before. Putting that in the context of a pipeline, right? We can be explicit. We can say, I have a pipeline Fibonacci. I want this logic to be in stage 1. This is the same as my logic before, except before I was just using a default pipeline, non-explicit pipeline, and default stage of 0. It's just shorthand. I prefer to always put logic in a pipeline just to be explicit about everything. So, any questions about that? Yeah. I'm not sure I caught all that, but in case it's the answer, the pipeline, you can have logic in any stages you want. The pipeline could have all its logic in one stage. That's perfectly fine. Right. I mean, I think that's what we did earlier with Pythagoras' theorem, right? We started with a one-stage implementation, and then we stretched it out over multiple stages. So that's the point, is that once you give yourself the context explicitly of a pipeline, you can very easily just take this mux and push it through a flip-flop, retime it through the flip-flop, and know that you haven't broken the functionality. Yeah. Yeah. Different pipelines, or yeah. Yeah, you can define any number of pipelines in your design. Those pipelines can communicate with each other. Is that the question? Yeah, I mean, we're going to start out just looking at simple examples that are one pipeline. Even the CPU that you design, it's all one pipeline. But, and we don't even have to talk about it for the entirety of the course, but you can split your logic into different pipelines, and those pipelines can consume signals from the other pipelines. So the organization of your logic into pipelines is more to match your thought process, right? You can take any design with, say you've got a design with 7 different pipelines. You could take all that logic and stick it all in the same pipeline. All of the logic that's sort of naturally flowing through a pipeline is going to look very natural in the code. Anywhere that you're needing to reference across pipelines, the references are going to explicitly reach across the pipelines, right? So it sort of stands out that you're communicating between the pipelines, which is a good thing, right? You want the natural things to look clean and the unnatural things to stand out. So, if you throw everything all into the same pipeline, you could sort of hide what's interesting, that there's stuff happening between operations that are, conceptually independent. So the choice of what logic goes into what pipeline, the TL-Verilog is not forcing you into any mode of design, but just sort of naturally partitioning the logic results in natural looking code. And it helps, that organization into pipelines helps to frame the way you look at the logic and think about the logic. So it's kind of taking things that in RTL you would put in comments and naming conventions and putting them into the syntax of the language, so that as a designer you can capture your intent in the structure of the code, if that makes sense. But we're kind of getting beyond, start basic.
The signals which all the signals which are in this context, the left hand side.
They're all in the pipeline. If the question is, how does TL-Verilog identify where flip-flops are needed? Right. So these references, like a squared, is a pipe signal, not a signal, right? So the declaration, which is sort of implicit here of A squared, defines, actually, let me jump over to microchip. It'll be pretty apparent there. So let me just make a separate pipeline with stage 1. It's simple. So here's my pipeline, right? And my assignment of my assumption that there's a bar, my assignment of foo, my use of foo, and the flip-flop. So foo, yeah. Hmm? Oh, I didn't. Okay, so now I have, these stages are independent. There's no signal that carries from one to the other. Right. Mm-hmm. This is the second stage of the pipeline. It's just that our logic, they're drawn that way in the diagram. There's no interdependency between the stages at this point because the signals are independent. I mean, we've declared that they are, but yeah, nothing about this logic. Mhm. Mhm. Yeah. So, I mean, just going back to this to make sure it's clear, right? The meaning of the term pipe signal is different from the meaning of the term signal, right? A signal in Verilog would be just this arrow, right, where we've assigned foo. In Verilog, you would explicitly have a flip-flop that has an input signal and an output signal. Those would all be declared independently. In TL-Verilog, the pipe signal is the signal as assigned and all staged versions of that signal, right? So we're assigning the pipe signal foo in stage 1, we're consuming the pipe signal foo in stage 2. That implies the flip-flop. This whole path is the pipe signal, same pipe signal, right? And of course, we can change this to a 20, and we get 20 stages. These here, you'll see them like this, right? Right. You can start anywhere. So here in this example, right, we don't have any logic in stage 3, for example. Just like this picture, right? So Mhm. Then it's another stage later, right? Another flop is another delay. That's a later stage in the pipeline. Yeah, so, you know, in this example, I didn't explicitly have any logic in stage 3, so there was no reason to have a stage 3 in the code, right? Of course, that stage exists. It just has no logic in it. So in TL-Verilog, you're very much, the vast majority of your TL-Verilog code is your logic expressions. The context is fairly lightweight, and then, you know, these other things, the signal declarations, the flip-flops, all this stuff sort of comes automatically. So it's very much just, what's the logic in my model? What's the context? I give myself context, and then, you know, the bulk of what I'm doing is expressing logic.
Then now I use signals, dollar
Mhm.
no, then what is that?
Yeah, so we can do that kind of thing here. Right, so you want to have and so what did you want? Sorry, this one?
Yeah.
Right.
If I have a statement at grade 5 and maybe another statement is a $310. So instead of this addition, I do the maybe the subtraction of $A and $B here.
Actually, I can probably copy this over to get exactly this.
Grade 5.
You wanted an expression of a squared.
$A plus $B.
Right, so we added this expression, which is an expression of B and A.
But A is getting already buffered. That means for each stage what I have.
Right, the fact that you have this expression that needs A and B says, you know, we need to have flip-flops on A and B to get it to this calculation for D.
That means this is facing that signal is going getting used in physical space. Until that stage, the signal will get
Right.
signal I can expect that signal which is generated after stage 2.
Mm-hmm.
Stops at stage 4.
Right. Yeah, the signal, the pipe signal is going to exist in every stage it's needed. So from the time that it's assigned to the latest use of the signal. And you can also use sub-ranges of a signal, right? If I only used bit 0 of the 31-bit signal in stage 1000, just that one bit would get staged off to stage 1000. Yes?
Number 8 will be 4, 5, 6.
Right.
What will be there before X3 to 1? What are those?
Nothing, they just don't exist.
What is the exact meaning of 4, 5, 6? That's the 4th, that means 4 is the 0th stage of the pipeline and first stage of the
Yeah, so the numbering is all relative. How you choose to number the pipeline, where you choose to start the numbering is arbitrary. That's up to you. If there's some association with another pipeline, you might sort of align the numbering, but it's the relative difference that matters. So you could take any TL-Verilog logic and renumber an entire pipeline by shifting the number scale, and that would preserve the functionality of the design. Actually, I have to be careful about that. So if you renumber one pipeline, you also have to reassociate links between the pipelines. But, you know, you pick a numbering convention and you stick with it. If you end up adding logic in the beginning of the pipeline, that just becomes negative stages, or however it works out. The absolute values just don't matter. It's the relative values that are important. So this is our Fibonacci series in context. And we're going to do the same thing with our calculator, right? So this exercise is just to put your calculator logic in the context of a pipeline, right? Which just means adding the calc and adding reset. In the MakerChip IDE, for convenience, if you need to indent code, as you will for this exercise, you can highlight the code and use Control square brace left and right to indent and unindent. All right. I'll walk around in case there are questions. Walk through this one with you if it wasn't clear what to do. It's a very straightforward lab. Okay, so all I'm asking is that you create yourself a calc pipeline, create yourself stage 1 in that pipeline, and put all of your logic in that context. Okay, that's all. And then we compile. Folks are handing out colored cards, so So we should have blue, yellow, red, and green. I'll wait for those to get handed out. And, well, I think pretty much everybody has at this point. So the blue card is just a name card. If you wouldn't mind just writing your name on. Fold the cards in half to make like a tent. If I could just, do you have a blue? You got robbed. So on the blue card, just fold to make a tent like this. Write your name on it. I'd like to know your names. And the other cards also make a tent. So these are just to help me understand when you're finished with an exercise, right? So while you're working on an exercise, leave the yellow card on top on your tent. When you finish an exercise, put the green card on top, ready to go. And if you need help, put the red card on top. That way I can just kind of scan the room and get a sense that we're ready to move on. Clear? That's a good question. One per person, but it probably could work out just fine, one per table. You all can sort of coordinate when you're all done and show me the green card. Either way you want to do it would be fine. You're naming the pipeline and stage. So put your blue card out in front where I can see it, or yeah, hang it on your laptop, works well. So if you're done with this lab, put the green card up so I know you're ready to go. Right.
That portion really give us here.
Yeah, so one thing to clarify for folks. So literally this lab exercise, you've already expressed your calculator prior to this lab. That logic just lands in a default pipeline in stage 0 of that default pipeline. All we're doing is naming our pipeline and being explicit about the stage number. So we're not changing the logic at all, right? So literally for this lab, all you do is indent this 2 and add these 2 lines. So it's worth clarifying this expression, which is where the recirculation happens. The output gets recirculated back to the next calculation to go through the pipeline, right? So all of this logic is for, we can say, one transaction, right? So a transaction enters our calculator. The transaction is the calculation. We do the calculation, and then we use the result of that transaction, right? A cycle later, that transaction goes from stage 1 to stage 2 through the flip-flop. At that point, that transaction is just defined by this out signal. And then that transaction affects the next transaction. Yeah, there's a flop where we cross the cycle boundary. Right, so in these diagrams, right, you'll get a flip-flop anywhere a signal crosses a stage boundary. In the case of out, right, out goes across the stage boundary, and then we use out from stage 2 in stage 1, so it loops back around. So we draw that loop outside the pipeline to indicate that there's no implied flop. You know, we're not visually crossing a stage boundary. So this, by pulling it outside the pipeline, we're implying a direct connection of the signal, right? So we have a direct connection from out stage 2 back to the stage 1 to be val 1, right? So when you put that in the context of the pipeline, right, I would read this statement as val 1 is out ahead by 1, okay? And ahead by 1 meaning I'm grabbing that from one stage ahead in its pipeline. So previously we called this previous. Probably from this point on, I'll start referring to this as ahead by 1 now that we have the context of pipelines. And now that I've redefined that with a second term, I'm going to later tell you that term's not right. We're going to start calling it alignment, but since everything that we do is in a single pipeline, we're just going to stick with the term ahead by 1. This green line, right? Indicating, so stage boundary, meaning separating stage 1 in this case from stage 2. Right, and implying the existence of flip-flops. Yes. Yeah. Right. Everybody comfortable with this? Yeah. Okay. Okay, I think we're ready to start up again. So now that you've got your calculator circuit kind of ready to go, we're going to jump into the starting point template that will allow us to work with tiny tape out. So go ahead to the GitHub repository for the course. If you don't have the link, it's github.com/stevehoover/GIAN-course. So we're going to open up this starting point code for the first one here, the calculator. It's good to right-click on that and open in a new tab so you don't lose the course repository. So that should load a starting point template for your work. If it doesn't come up for anybody, let me know. Maybe it's not going to come up for me. Slow. Okay, so this template uses something we call the virtual FPGA lab. So I guess we haven't talked yet about the visualization feature. So MakerChip has a feature called Visual Debug that lets you represent your circuit simulations. We didn't talk about this, right? No, okay. Lets you visually represent your circuit simulations in a way that makes sense to you. We use that framework here to create a virtual FPGA lab. So you've got your FPGA board. And I think we're going to need these handed out soon. So maybe IIT, if you can make sure everybody's got the board. And we can zoom in here on the logic that we have in our FPGA. In our case, we have a calculator. This template is providing you the visualization for that calculator. So I can step through in simulation with these controls and see that I'm doing 0 divided by 0, which Verilog defines that as a 0. 0 times 0 is 0. If I step through far enough, I might see something interesting. So I'm just going to let this play, right? Doing all these operations on 0, producing 0. Let's jump this ahead and see what we ever get anything interesting. We don't? Let's see. Why is that? That is because we don't have any logic in here. So we'll address that soon. But let me show you what's in the starting template. Most of this, I'm not going to explain the whole structure here, right? The point is the logic that you're working on, and we're going to focus on that. But just a few things to point out about the starting template, right? We have our standard structure for a TL-Verilog file. We're going to use macro preprocessing, so we need to call the M5 library. We have some settings here that are also using macro preprocessing to configure the work that we're doing. So we have a definition of the name of our top level module that we're using for tiny tape out. We're targeting an ASIC implementation. I actually thought I had removed that, but I don't think it's doing any harm. This is setting the visualization to show us that we're in the context of an FPGA, and we'll talk about debouncing inputs later. So, I mean, none of this is important. We're just going to focus on the logic, but just so you're aware that there are some settings. This is using the settings to set other variables, not important. This is including the libraries that are used for this template. So the first being the tiny tape out environment that gives you the visualization of the tiny tape out FPGA. The second being the context for the calculator, which gives us the visualization for the calculator. And so instantiating the calculator visualization, and we have no logic yet. This is just a template. So all we have for logic is hooking up the output connections. So here we're hooking up. So tiny tape out has 8 output bits. These are those. So this is a reference to the Verilog module interface signal UO out, which is those 8 signals. And we're initially just assigning those to 0. We can see that in simulation. This is our 7 segment hooked up to this value, and we see that the segments never light up. So for example, if I drive this with FF, we'll see those segments are all lit. We'll see the design is broken. That's not a binary value. Let's try hex. So all the segments are lit up. So that's our output, 8 output signals. In the version of tiny tape out that you're going to use ultimately, we have 8 additional outputs that are, well, we have 8 additional pins that are bidirectional, either input or output. So we have output signals here for those, as well as the enables for those that tell us whether it's an input or an output pin. The FPGA boards that we have don't have those 8 inputs. That's why we have the condition here that's saying if we're targeting the FPGA platform, we don't have these. You know, don't worry about the syntax, but this is conditioning off those assignments if we're building for the FPGA boards. And then the template has our standard maker chip module. We have a little bit of kind of test bench code. This is just initially driving random values on, let's see, on UIN, which is our 8 input bits. This is just connecting those to random. And this is carrying through the output signals in this module. So again, nothing important. This is the instantiation of our tiny tape out module. So basically, the top level module in MakerChip is our test bench for the tiny tape out module. And then the tiny tape out module is here. Okay, so this is the standard module interface here for the tiny tape out projects. Again, our FPGA boards are previous generation. Those don't have the bidirectionals, so there's some code generation stuff here to condition off those signals for the FPGA compilations. And this is instantiating the FPGA lab that provides us the visualization. Okay, so again, none of this context really matters. We just focus on the logic. This is giving you the environment to work in. But just to give you some context on what you will come across in this file. What else is important here? I think that's good. So the first lab is to take the calculator circuit that you have and drop it into context in this template. Your code goes here. So This lab is just to grab your calculator code from here and drop it into the template. All right. I'll give you a minute to just read this, and then I'll do it myself. You can just watch and follow along. Well, I'll just do it. You can follow along now. So find the calculator starting point template. Open it up. Hopefully you've got that all open. Paste your calculator logic, including the calc pipeline, into this template. So I've already selected it. Copy. Paste. Compile, debug, explore. So that should be all there is to it. Compile. Let's see how we do. Looks like everything is clean. The log is clean. So as long as you build and your log is clean, I guess this says explore viz. Nothing is actually hooked up, so I don't. Well, okay. So I think the visualization is driven off of your internal signals. So I think we can see that the calculator is operating. I'll just give you a second to finish the cut and paste. So once you've done that and your compile is successful, you should see in the visualization that you're able to step through and see calculations. So 7 divided by 1 is 7. We're, at this point, just getting random stimulus on the inputs. 1 times 3 is 3. Looks like my calculator is fine. 3 times 6 is 12. Well, that looks odd. So these numbers are hexadecimal numbers, right? 3 times 6 is 18, which in hexadecimal is 12. Okay, so you can take a minute and play around with that. And of course, once you see that your calculator is working, just put your green card up so I know you're ready to move on. Step through and make sure that it's showing. set. So and it's not finding. So in case you use different signal names that the visualization is looking for, I'll just leave my code up here for reference. I think mainly it's looking for out and probably val 1 and val 2. So if you update your circuit to use those names, you should have better luck. Okay, so one more thing now, also available to you from the course repository. There's a link here for reference solutions. So again, right-click, open in a new tab. If you closed the GitHub repository accidentally, github.com stevehoover/GIAN-course. So what's opening now is some reference solutions to all the lab exercises. So all of the lab exercises from here on out, there are reference solutions which you can refer to. I encourage you not to. I hope that everyone's able to get through this course without relying on the reference solutions. Maybe once or twice when you have some issue. If you're looking back at things in the evening when folks are not around, you have the Slack channel to ask questions on as well. But you also have these reference solutions to lean on in times of desperation, right? So what you'll see in the reference solution, the main thing is this line here where you're setting the lab ID. So in all of the coming lab exercises, you'll see a lab ID in the lower right corner. So if I want to see the solution for this lab, let me go to a later lab. Let's try C equals. Just type the lab ID and compile. And this is going to build the solution to that lab exercise. You're not going to be able to see this. Actually, how did I set this up? Okay, you are going to be able to see the source code. So you have access to everything. If you just wanted to get through the course and declare success, you could cheat and use the solution and just cut and paste. But that's not why we're here. We're here to learn, right? So it's all here and accessible. But again, I expect you not to use this. You can see the behavior in the visualization to help understand what the lab was trying to get you to do and use the waveform. What I would encourage you to do is not lean on the code, but instead, if there's something you don't understand about a lab, you can lean on the diagram, lean on the waveform to understand what it was the lab was asking you to do, right? Use the waveform to understand the behavior that's expected. And maybe check yourself by just checking the reference solutions visualization. As maybe you're working on a lab exercise and the visualization looks wrong to you, but you're not sure. You can open up the reference solution and see what the visualization shows in the reference solution. Yeah, so that's available as a resource. Especially since this is, sometimes I conduct this virtually and I'm not here as an instructor to help the students. So it's useful in this format. It shouldn't be so necessary. But just so you know, it's there. Talked about this. So the next lab is to connect the outputs. So right now, you've dropped your logic into the template, but we haven't hooked up the inputs, we haven't hooked up the outputs. So the next lab is to hook up the outputs, and the lab after that is to hook up the inputs. And then we'll have a complete tiny tape-out design, a functioning calculator, and we can play around with that on the FPGA boards. Okay, so this lab is to drive the output value of our calculator on the 7-segment display. The output value of our calculator is an 8-bit value. We only have 1 digit that we can display, so we can really only display 4 digits that are coming out of our calculator. Okay, we'll live with that. So just hook up the lower 4 bits of your calculator to the 7-segment display. And of course, we want to represent that value as a hexadecimal digit. So we need a 7-segment decoder to go from the 4-bit binary encoded number to the segments that need to light up. Okay. So the 7-segment decoder, first we're going to just extract the lower digit from our output. So that's just this, I may as well go full screen here. This first line, digit 3 to 0, is bits 3 to 0 of the output, just to extract those 4 bits as its own signal. And then an expression for UO out, right? So UO out is the Verilog interface signal for the tiny tape out module. So we need to assign that Verilog signal. And then the expression that we're going to give here is the expression that will produce the right lighted segments. UO out is an 8-bit, right? And we've got the segments labeled here. This is bit 0, bit 1, bit 2, 3, 4, 5, 6, and 7. We're not going to use the decimal point, so output 7 will always be a 0. We'll code this as a complete assignment for 8 bits, but all the cases you'll use that bit 7 as 0. So this expression is if the output value is a 0, drive the bit pattern that represents this 0 pattern, right? If the output value is a 1, drive this pattern. If the output value is a 2, drive this pattern, right? So what sort of structure are we going to need for that if then else case kind of structure, right? It's a mux, right? We're multiplexing all the possible input cases with the output values that they should have. The active is lit, right? So all the segments that you want to light up, you drive with a 1. Ones you don't want lit are 0. It's important to first remove the old assignment of UO out. Verilog has a lot of quirks, one of which is the Verilog tools tend to be perfectly fine with multiple assignments to the same signal that would collide with each other, and they'll just randomly use one and not the other. If you forget to delete UO out, you're going to get a 0 assignment. None of your logic is going to be visible in simulation. So make sure you remove the old assignment to 0 of UO out. And once you have your logic coded, a good way to test, obviously the logic that you're coding is just a whole bunch of bit patterns for all these cases, right? You need to make sure you got all those bit patterns correct. So a good way to test that is to drive your calculator with +1. Every operation +1. And then your calculator is just going to increment through all these values, and you can check the visualization to make sure that you're getting what you expect. Okay, so you can drive op and val2 to represent perform a +1 operation and let that simulate. All clear? Any questions about driving the +1? Yeah. So the goal here is just to test that all of the bits that you've defined are correct, that each case is driving the right bit pattern to represent the number the way that you expect, right? Very easily you make a mistake and accidentally drive a 0 for this segment of the 9, right? It's going to show up goofy. So just to test each one of these cases, if you set your calculator up to add 1 every cycle, it's going to iterate 0, 1, 2, 3, 4 on the output. And so with that simulation, you can easily check every output value, right? And so you can get that behavior by, right now, op and val2 are inputs, and they're left dangling. So you can just temporarily assign them to perform +1 always. Right? If you tell your calculator always perform the operation plus with a val2 of 1, it's just going to keep incrementing. Okay, so there's no learning without struggle. If you are struggling, I'll help you get started here. Let's see. That's my reference solution. So if you're having trouble, right, we need to go case by case. Um, if the if the digit is a 4-bit 000, then we want to drive the bit pattern for the zero that represents 0, right? And that's going to be all the segments are 1 except for 6 and 7, bit 6 and 7. So we want an 8-bit binary 0011 1111. Otherwise, the rest. Yeah, this one here.
Like this?
A card like that is fine. I mean, you can print them on a full sheet. Is fine too.
So, do you want this back to back or how you want?
The intent was back to back, but think most people are all set, but I'll walk through the solution and then it'll be perfect time for lunch, I think. Okay, so here's my expression for the for UO out to drive the 7-segment display. Right, I have my assignment of digit, checking each pattern of digit. If digit is all zeros, 0 value, I want to drive the 7-segment display with the pattern that's going to represent a 0. And likewise for all other input values, the last input value, the F case, becomes the default. If the if digit is not 0 through E, all that's left is F. So we just leave that as the default. In the ternary expression, every if then needs an else. So this is the else of the final ternary expression in the chain. So then driving the inputs so that we are constantly adding 1. Add is an op of 0. So I drive the operation as add, and the value I want to add is 1. So I updated the expression for val 2 to drive an 8-bit value of 1. Okay, and at this point, simulation is adding 1 to the output and showing me all the patterns. Right. So after lunch, we'll reconvene at 2:30, right? At which point we'll hook up the inputs to our calculator so that they're appropriate for running on the actual FPGA board, and then we'll play around with the FPGAs. All right?